अच्छा, so I was asking this question कि इसमें what is wrong? Not, I should not say wrong, but what is not really optimal from state machine perspective or from even the design perspective. और उसमें ये है कि whenever you are using an always at pause edge clock statement, everything that is on the left hand side with a non-blocking procedural assignment means it is going to be a register. Okay, so though I want this write pointer to be a register, I need this read pointer to be a register, I need FIFO count to be a register, because if you remember, I have made uh, the three registers: read pointer, write pointer, and the count. But then the error signals are need not to be registers. So these three error signals, they need not to be registers. They should just be the status of the FIFO. So, but it has made them as a register, uh, as because they are appearing in the left-hand side of the procedural block. So this this is and also this value, once it is reading, it is putting in into a register out data. I want just this value to just go out from the memory. It's going into a register. So anybody who is using this FIFO would get it in the next clock cycle, which may be fine. I'm not saying uh, something very specifically wrong, but I wanted this to be just part outside the procedural blocks. Okay, so almost similar code was generated by the. Let me try generating it with the. Uh, so almost same, but it should have like it has not reset these registers. So but this is okay. So what I asked it to do was, so the this is the description of the FIFO: do this, do this, do this, do this. Okay. So this we have seen. The good thing it has done, especially the ChatGPT, it is parameterized 16. You can change this number, and these are also parameterized based on the depth. It will take log base 2, assuming depth is always going to be a power of 2. So whereas the Copilot has just fixed it to 4, and for which you can always go and change this. I mean, it's fine that you can, or maybe another parameter that you can define. Uh, so it has issue was that all these flags were set to 0 in an initial block, which obviously must not be part of the RTL code. And then the same thing, the error signals were 0, 0. So I did not like, I asked it that there should not be an initial block in the RTL Verilog code. So if I show you the chat GPT, so this is what it has generated. And then I ask it, there should not be an initial block in RTL code, move it to the reset part of the synchronous procedural block. I said, if you want to reset something, we don't reset it in the initial block. We do this as is done by the Copilot. So you should able to figure out these things and then ask if there you see such an error, reprompt it. So and ask it that no, this is not right. Just move this thing out instead of coding it yourself. So I asked this thing, and then it did that. So it is post edge reset, and then it has resetted all these. Same thing, almost the similar code what you have seen in Copilot, the FIFO count and read pointer and write pointer, but all these are registers. And similarly, it has like if you have read and write at the same time, it is going to generate an error. If you are writing and FIFO is already full, it is going to generate an overflow error. If you are reading and the FIFO is empty, it is again going to generate an underflow error. Otherwise, it is going to write, increment the right pointer, and doing the count plus plus. It is also reading, writing, and also doing the modulo depth, modulo depth. I think that it has also done the modulo once incrementing the pointer. No, it has not done that. So that definitely is not right, which you will only be able to figure out once you run it, fill the FIFO, and you will realize that it will work once, but then the counter would not be going back to the 0, 0, or it might have forced it to go to 0. FIFO count, yeah, if it is 0, uh, so the pointers, maybe once the count is full, it might have done that. So I'm not doubting it. Yeah, no, it has not done it. So this is a good code. So I liked it. But what I did not like here again is that these overflow, underflow, and error write should be just wires and not registers. So why not to assign them values outside the procedural block? So let me just say the same. First, let me ask it to fix uh, uh, the increment to read and write pointer shall be modulo with n. So I said, yeah, I understand it should be modulo. So now it has corrected it. So as you can see, it is modulo with n, so that the pointer, once it comes back, it comes to the last point, it should start pointing to the start of the memory to ensure that it is circularly just keep on reading, writing without you worrying about resetting it to the. So this is, it has made this correction, and then I wanted to make another correction, which is about, so I just copy it from the, so I'm asking it to move them to the assign block, and I want to see whether it does that or not. So yeah, it has also done it. So it has moved it whenever the count is equal to 0 and there is a write. If I assert write, so it will assign it to the, so the overflow flag is set, and if it is count is 0 and I read, underflow is set, and if read and write at the same time. So this is now is good. So we are seeing like by what I want to here demonstrate is that you need to keep on, if you only understand that how the Verilog works, only then you can prompt it to do this, to do that. There should not be an initial block in RTL code, move it to the, so it has done that. And then I ask it to issues with flags, they are all registers. So I ask it to do prompt, can the overflow, underflow can be outside the always procedural assignment. It has done that. We have seen it there as well. All flags are now assigned with assigned statement. So I'm slowly getting the code in a shape that I really like. So, and then this was the last thing. Issue was with read into, I don't want to read my output value into a register. This particular out data is going into a register from memory. I don't want to do that. So I ask it with the test bench. So I first developed the test bench, but the test bench has no monitor statement. I ran it, so I did not like it. I asked it to put a $monitor to display all the input and output of the modules along with the internal variables in the FIFO module. So this is what I ask it to do. And I also ask it to put count out data should not be assigned to a register, must be outside the procedural block. So So this is out data assigned to output wires and not to a register. So it has done that here. Output data is now assigned to a register if count is uh, greater than 0. I'll read a value, but if it is 0, it will just read 0 because there is nothing in the out data. So it is just reading 0. So this is a pretty good coding. And I've seen the Copilot and the ChatGPT doing the same. As I told you, now we can have even a test batch. So just asking it to, let's ask Copilot to generate a test bed. So it's very good. It is just generating FIFO write assert, and then it has read assert, and then so it just checked, and you may ask it, no, do initialization, write, read. It's just very fundamental checking has done, but as you can see, there is no display or monitor statement even if you run it. You have to look at the waveforms, but once I asked the ChatGPT, it generated a good test bench, checking all the conditions, especially writing into a FIFO. It checks the overflow condition, whether if you write, and then 16 times, and then you are writing it again. It is checking the overflow condition. It is checking the underflow condition. It is checking the read and write assertion. So FIFO write and FIFO read asserting at the both time. So I honestly, I liked it. So I ran it on, here is my simulation. So these are the simulation. I first ran it, and then I asked it to write into monitor. So if you can see here, you are asserting right. Okay, asserting right, it is and not read, so there is no error, and its in data is getting into memory. The out data, you are seeing the first value, and then you have the uh, neither overflow, no error. Right pointer is increasing, and after 15, it has gone to 0. And now, another right here, flow flag. And so, good code that uh, happening. So this is the emulator, and the code was nicely written. All these assigned statements are here, which are not part of any uh, synchronous procedural block. And then we have a classical procedural block with the register, and then condition. If write and then FIFO is not overflow, then it is going to write, and similarly read is going to read in a similar manner. And then the test bench, and the test bench, and having a monitor. Monitor is always a good system level task. Remember, I told you that monitor gets activated whenever anything in this changes. So it's always, and also definitely maybe next time we also start seeing the waveforms that you need to know to read the waveforms. But good code. Uh, it has one, which I told you earlier, that just for the sake of making yourself thinking in terms of controller and the data path. Okay. So if I ask you a question, what should be there in the controller? What type of signal should the controller generate, and what should be there in the data path? If anybody can answer this question, what should be in the data path, and what signal the controller should generate for the data path. D. Anybody? लोग हैं ना इधर?
जी सर हैं।
अच्छा चलिए मैं खुद बता देता हूँ. अच्छा, I want the data path to have the memory. Obviously, I want the data path to have the memory, which is the FIFO. I want the data path to have all the three registers: read pointer, write pointer, and the count register. Okay. And I want just two signals controller, the two sending two signals. One is write enable, yes, you can write. And read enable, yes, you can read. Data path. So data path should only know, yes, I can write, yes, I can read, yes, I can write, yes, I can read. And it should send its status of the count so that its controller should know that whether it is an empty state or it is already full, and should generate all the status to anybody who is using it. Status signals are if it is underflow, overflow, and read write error. So three status signal. It should get a request to write, and it should get a request to read. Okay, so it has a state. So there is a state register. So state machine always has a state register. Okay, now I'm thinking in terms of a controller and a data path. And so the data in is coming here, which is 32-bit of data, and data out is going here. It is also 32-bit of data. If I ask you a question that how many states should be there of this FIFO? कितनी states आपको लगता है हमारे पास होनी चाहिए? मसलन एक स्टेट है कि FIFO empty है E, और कौन सी स्टेट हो सकती है?
सर FIFO हाफ फुल हो सकती है, फुल हो सकती है, हाफ फुल हो सकती है,
फुल हो सकती है और पार्शियल हो सकती है. ये थ्री स्टेट्स. So because these are the three states which are important. If FIFO is empty and there is a read request, I must generate an underflow condition, underflow flag, and must not read anything. So once the user sees, anybody who is using this sees there is an underflow flag, he will understand that I have asserted a read where there is nothing in the FIFO, because somebody else is writing in the FIFO usually. So FIFO is written by somebody and read by somebody else. So he says read me and says there is an underflow, there is nothing in the FIFO to be read. Okay, so full is if write and the person has not reading anything, and the guy who is writing, the FIFO is full, and he writes another thing, and it says, oh, there is an overflow flag. And usually because there will be confusion, so somebody reading and writing at the same point may be confusing. So you're saying don't read and write at the same time. So there are going to be three states. One is empty, the other one is full, and the third one is it is partially empty, and partial filled. So it is partially filled, so you can read, you can write without worrying too much about this. So this is, a design which I would like uh, is to have. I want to have it a controller. I want to send the control signals, and there seems like two control signals, and the request for read and request for write is coming, and I am generating the three status. The controller is generating the three status. So always I would like you to perceive a design in this fashion: a controller and a data path. Okay, so these are the three registers, and this is N deep memory, and which is 32-bit wide. So 32-bit wide memory, 32 and 32. So this looks good. So I now prompted ChatGPT, can you convert the design into two parts, controller and a data part? Control the state machine with three states, FIFO and FIFO partially full, FIFO full, based on the FIFO count. The state machine also generates different status signals based on the read and write value of the. These signals are FIFO underflow, FIFO overflow, and an error write. The data path keeps the FIFO itself and all the read and write pointers along with the FIFO count. This is what I have the ChatGPT. To do this, let me go back to ChatGPT, uh, where I have asked it to. What happened? I want to actually give the same. I want to see what happens if I give the same. Actually, because of okay, so it's doing it. Yeah, it has like three states: FIFO empty, FIFO partially full, and FIFO full. And the FIFO controller, then this is the FIFO controller case. And then this is the FIFO data path. So it has done, and then this is where you have the controller and the data path. So pretty much it has also a kind of has done that. Same as what the once I asked the Chat GPT very nicely. I really got impressed that it has now FIFO module, and the FIFO module has two parts. As we always going to draw these two parts. One is the controller, and the other one is the data path. So every design, once we are designing the architecture, that will help you to design a good architecture. Okay, to break it down into two parts. One is your control, the other one is your data path. Try data path to be dumb, very dumb. Okay, that it must get instruction from the controller to do things and should send its status back to this, and all the instruction it gets from outside, and it has status of the design. That has the status, which is its state, and which it keeps on updating based on the input and the current state, and it generates these status signals to the person who is using it, and to the data path it may be getting something, and it may be doing something and getting something out. So usually this is how the design is. If you look at this, it is precisely the same. Is this a data path? Nothing else in the top module. So this is your FIFO. FIFO has a clock, the reset, the FIFO read, FIFO write, in data, out data, and the three flags. So yes, this is precisely what I wanted my top level modules to have. There are internal signals, all these 3 pointers, internal signals coming from which are in the controller. So I have the data path, which has all these things, And then I have the controller, which has all these things, primarily my overflow flag, underflow flag, FIFO count, write, read, and reset some of the inputs and the outputs. And then once I saw the data path, it is very dumb. Why it is? It's only it's reset. If you assert reset, it just reset all the three registers, and then all it cares is whether you have. Oh yeah, first it generated where there is a control in the data path as well. Say FIFO write, then checking if there is a FIFO write and FIFO is less than depth. So I did not like this. I said, no, don't put any control in my data path, okay? And the controller was okay because this is the path where you have, if it is reset, you reset the current state to the FIFO empty state. Whenever there's a reset is asserted, otherwise next state becomes the current state. Always going to be like this. This is the cloud. The intelligence is in the cloud. So there is some input. There is next state. Next state goes to the state register. And based on the current state and the input, you generate this and the output, which is going to the controller, the data path. So it is precisely doing this. So the cloud is it is the initialization. Remember, it is important. Otherwise, it may instantiate latches. So whatever variables you have in the combinational cloud, make it a practice to assign them a default value before you enter the intelligent part. So it is based on the current state. So based on the current state, it is going to check the input. So this is the first state. If empty, FIFO is empty, and somebody assert read, you are going to generate FIFO underflow flag. Okay. And if there is a write, if state is empty, so next state is going to be the FIFO partially full state. So interestingly, it has also handled the case where there's only one register in the FIFO. You need not to, but it has handled that as well. It is the case where it is partially fill and read and write. Somebody has asserted read and write to generate the error. So important is I ask that controller shall generate read valid and write valid signals for the data part to operate without checking itself the condition. So I don't want any intelligence in my data path. I want it to just get to signal. Yes, you can read. Yes, you can write. That's simple. So I ask it, so it has done that. So I was really happy to see this. The controller has all the logic and controller is generating two signals. There is a valid read and a valid write. That's all. So this controller has done it. So I was very happy to look into this state machine. And then the data path is so dumb. It is getting whether it can read or write. That's it. It's not going to check anything. So as you can see, it initializes all these three registers, write register, write pointer, read pointer, and FIFO count. And if write is valid, it will write. Whatever is on the in data bus, it will write it into the memory pointed by the write pointer. And then it is going to increment the pointer and modulo with depth and increment the count +1. Similarly, if read is valid, it is going to increment the read pointer and modulo it with depth, and count is -1. It's a perfect code to my liking, that the data path is dumb and all the intelligence is in the controller. So I would very focus making sure that I don't mix any intelligence in the data path and intelligence in the controller. And then these are the two parts where you have the controller and the data path, and that's it. And it just would work. So I have like several other state machines. I'll not get into these, how I have designed them. This is actually part of our processor where it has a variable length instruction dispatcher. Sometimes an instruction comes, which is a 16-bit instruction. Sometimes instruction is a 32-bit instruction. And we never wanted the controller the program instruction decoder to wait for the complete instruction. So it has to always fetch a complete instruction. It was a pretty complex state machine. And I think Arsalan coded this at that time, Dr. Arsalan now. And he has made really his name in VLSI design. So this is the state machine from that time. Now, now what I intend to cover in this remaining time is something again very fundamental to algorithms, that how you are going to represent numbers. Usually once you are coding it using Python or MATLAB or C, and you are least worried about these things to understand, but once you are implementing it in hardware, you've got to be very cautious that how you are representing your numbers, because 16-bit architecture or data set will take a 16-bit of memory, but if it is 32-bit of your algorithm uses 32 bits, so your hardware will be doubled, more than doubled, because multiplication will take even more area. So something which is 16-bit versus something which is 32-bit in Python, in MATLAB, there is hardly any difference. You are, but in or 64-bit. 64-bit is floating point, double precision floating point arithmetic is a 64-bit, or single precision floating point is 32-bit. 64-bit means uh, a lot, humongous. So most of the simulations that you are running, they are on 64-bit numbers. In hardware, especially once you are mapping them into silicon, 64-bit is not even an option usually. Even you try not to use 32-bit, try to get to 16 bits, because you're doing a lot of things in parallel, a lot of multipliers, a lot of adders, hundreds and thousands of them. A 64-bit multiplier would eat up a lot of area. And then handling, especially floating point addition, multiplication is so complex, and you want to make them run very fast. So there are many challenges. So the first challenge, once you are converting an algorithm into silicon, is that how you are going to represent your data. May it be an image, a video. So usually the input is known to you. Input is known to you. If it is a video, you precisely know that it is RGB. Every pixel as 888 24-bit, or it is 12 12 12 bits, and how many pixels are there in a frame. So you precisely know the size of your input. Uh, and if it is analog to digital converter, you precisely know the precision, because once you go and buy these A to D converters, you will know that you don't have many options. Usually you may get something which is sampling at 12 bits. Same is the case once you have a system, you are processing. Though here all your computations are at high precision, but once you're going to convert it back, playing it on a speaker or displaying it on a screen, okay, you cannot do like 64-bit. There is no D to A converter almost, which can convert 64-bit numbers. Usually they don't support these many levels. So there is a restriction. And for example, for images, if you are ultimately going to be just every pixel is going to be 8-bit, so there is no point in having arithmetic, which is doing 64-bit of precision. So because your output is always going to be few bits. So it is same as you say you want to return me 10.111110 rupee. Okay, and you say I don't care about this because I'm only dealing with rupees, and rupees is either 1 rupee to 10 rupees, and even now people don't care about 1 rupee. But this type of precision is not required. So why to just do such a high precision in your internal computation, maybe two places to decimal should be enough for you to see, to truly reflect that. And even if there is 1 rupee going this side or that side, you don't mind, instead of spending a lot of money in doing high precision arithmetic in hardware. So, and especially this is the case for large language models. The problem with large language models is that they have billions of parameters. If the billions of parameters are in, let's say, floating point 32-bit, that's how they design it. But dealing with 32-bit floating point numbers and billions of them is very challenging. So that's why you will find a lot of research in quantization, that let's quantize this 32-bit number into 8-bit, and there are even papers which talks about 4-bit. And 4-bit means there are, for every number you have only 2 raised to the power 4 possibilities. Okay, so every parameter has to be one of the 16 parameters that you have. 2 raised to the power 4 is like you have only 16 possible numbers, and whereas 32-bit floating point means you have 2 raised to the power 32 different numbers. Okay, so a lot of people are focusing on converting these quantizing the large language models because of the amount of computation required to handle this. And same is the case with deep neural networks. Again, you end up having so many number of multiplications and additions, and these are the fully connected layers, and all the fully connected layers, the amount of weights that you have. So people are kind of cautious about the precision. So understanding this is very important from architectural perspective. So there are usually two ways to represent a number. One is a floating point in a floating point format. So usually once you are running your simulation, uh, you have your all numbers, all the variables are in floating point format because it's so easy to code, because you need not to worry about the underflows and overflows, and usually and the because the composition of the floating point itself would increase the dynamic range of the numbers to values. Usually your computation will never go beyond those ranges. Okay, so it's ease of coding where you are focusing on your algorithm, not focusing on these issues, but they cost a lot in terms of area, speed, and power. So usually you don't want anything to be in double precision arithmetic. So either you lower the precision as a floating point number, or you go for fixed point arithmetic. This is ideal, and this is only possible if the dynamic range of the number is not that much. So you can basically squeeze in all your variables to fixed point format. And fixed point format means that your decimal is, you got to fix the decimal at one location. Fix the decimal. Let's say you say 4 digits on the integer part and 12 digit in the fractional part. So this, once you fix it, it remain fixed for all the variables unless you change it yourself. So you have to move the decimal by yourself. And that is not easy because a lot of simulations has to happen before you understand where you should you place your decimal point. So fixing the place of decimal will definitely make your hardware very simple, very low power. It'll take less silicon, because now, though you are doing floating point arithmetic, but fixing the decimal would convert them into just integer multiplication, integer addition, and that is going to be very, very helpful in designing an architecture. So, but then you have to deal with issues like once you multiply two 16-bit numbers, you'll get a 32-bit number. What to worry about that? What to do that? Code becomes very less readable because the decimal is only in the comment. That comment will say my decimal is after the 4 location, and but otherwise you are using just integers. Okay, so because you are using integers, so anybody who is actually decoding, debugging, would have hard time in figuring out what this actual number is, because you have converted every number into an integer which only you know, or you have put a comment that where the decimal is. So after knowing the decimal, only then you can convert it into a floating point to see whether how it relates to your simulations, which would happen in the floating point format. So these are the challenges, but still people would prefer fixed point arithmetic over floating point arithmetic because of the reasons I've told you. That once you're doing hardware design, doing sometimes you have no other option but to do floating point. Okay, but you have mostly done by algorithms are all floating point algorithms, and anything that goes you need to convert it into fixed point. Anything that goes on digital signal processors, that is also usually converted into fixed point, because most of these DSPs, though they are floating point processors as well, but there's a difference in cost and the power dissipation, and so you convert them into a fixed point. So it just says the same what I've told you. So specification, you get design specifications, then you run these simulations and algorithm development, and then once you have decided that this is what you're going to map in hardware, so you map that in hardware. So there are the floating point digital signal processors even for the software, but preferably. And remember, this is because once you're going to play this back, there is only 12-bit precision, and you say, why should I, just do a 32-bit precision or even 64-bit precision algorithms once I know that I can deal? And there is also a fixed dynamic range of numbers. So there are many motivations for people to use fixed point, to go to the trouble and pain of designing your algorithm in fixed point. Okay, so to understand the numbering, that how it works, and this you must already be knowing, and just must be a refresher that two's complement arithmetic is used in every computer that we use. There used to be and there is once complement arithmetic, but usually nobody uses this. Sign magnitude, nobody uses this. Sometimes in hardware, if we are dealing with fixed numbers, like the coefficients, and if they are fixed, canonic sign digit is also used, where the bit is not only 0 and 1, it could be -1, 0, and 1. So you have -1 is also an option. Why? Because if you have 15, so there are 4 1s, 4 non-zeros, but 15 is also 16 minus 1. So you can write it like at location this -1, 0, 0, 1. So this bit has a weight of 1, this bit has a weight of 2, this bit has a weight of 4. Sorry, then there has to be another 0. I can put that 0 here. Weight of 8, and then this has a weight of 16, -16. So because you have put a -1 over it, it becomes -16 plus 1. It makes it equal to 15. So 15 has two ways to represent. One is 15 is all ones, and another 15 is -1, then 0, 0, 0, and then 1. So that's how you can represent minus. So two's complement arithmetic is normally used, and because two's complement arithmetic, you need to deal with positive numbers and you need to deal with negative numbers. How you deal with them? The most significant bit of these numbers has negative weight, and rest of the bits they have positive weights. Okay, so that's how you represent two's complement arithmetic. Like if they are 4-bit number, so this bit has a positive weight of 1, this bit has a positive weight of 2, this bit has a positive weight of 4 because going in the power of 2, and this bit would have a negative weight of -8. So a 1 here means -8, and 1 here means +4. 1 here is this, and 1 here is this. So this -8 plus 4 plus 2 plus 1, 1, 1, 1, 1 becomes -8 plus 7 is -1. So -1 will be written as 11111. So most significant bit in 2's complement arithmetic has negative weight. So a negative number will always have its most significant bit equal to 1, because that's how you will represent a, a 2's complement number. Okay, so this is the example. It is -8 plus 2 plus 1. It becomes -5. Okay, so so equivalent representation. So this is how the numbers are represented. There is definitely an issue in this representation, that the 0 is considered as positive, not negative. Okay, so there is no negative 0. So you have a 0, which is all zeros, and because sign bit is positive, so this is considered as a positive number. 0 is considered as a positive number. So that's why you have one extra positive number. And then once you have here 1, and then you have the negative numbers where the sign bit is 1. Sign bit is 1, you have negative number. So you have 1000 is -8, -7, -6. So this counting will, and this is another problem. Counting will start from 0, 1, 2, 3, 4, 5, 6, 7, and once it is 8, actually it is -8. So there is this much. If there overflow has this big a penalty, because a 7 will, adding 1 will go to -8, and then it'll go -7, -6, minus this, and again 7, it will go down. So that's another issue with the 2's complement arithmetic, that an overflow has a big penalty on your computation, as +7 will not become -1, rather it will become -8, negative number on the other side of the, so the entire dynamic range of numbers, the error induced by just a little overflow is big. So 2's complement arithmetic, so always you need to worry about to avoid overflow scaling and sign extension, changing a 4-bit number into an 8-bit number if you're worrying about the overflows. Uh, So sign extension is like if you have a 4-bit negative number and you want to make it an 8-bit because you are worried about the results may overflow in your algorithm. So you have to extend it by putting the sign bits. So replicating the sign bits. So -8 as 4-bit number is 1000, and -8 as 8-bit number is 1111110000. Okay. So they both have, like, as an unsigned number, very different value, but as a signed number, they are the same. So these type of confusion, especially once you are looking in your simulation, and simulator is showing every number as a positive number again, uh, cause you a lot of problem to figure out what this actual number is. But remember, and that's also once you are scaling, sometimes you drop all the redundant sign bits. So any bit after this, once you have a string of ones, all these bits are not adding any value into the number. So many zeros on the left or many ones on the left in the sign bit means that uh, you are wrongly representing your variable. It does not have that much dynamic range. Let's say your number is only varying from -4 to +4, and but you have 12 bit to keep them. So all the time you are going to say 11111111, because your dynamic range is so small that your number basically does not require a 12 bit or 16 bit precision. So now comes the especially this is what is used in LLM. All these parameters are floating point number. And why floating point number? Because floating point number, once you're training the parameters and it is going through all the back propagation neural network, where you are going through gradient descent algorithm. Usually, I was once looking at the parameters of a large language model. This humongous dynamic range. Like a number is positive on one side with some very high power, then it is negative on the other side. So converting them into fixed point is almost impossible, because if you have such a dynamic range of numbers, then there is no point in fixing a decimal, because sometimes the entire part is integer, sometimes the entire part is fractional. So how should you decide? And there is a variable which is just changing its value. So usually their fixed point even does not become an option. That's very bad. Or even if it is an option, um, again, as I mentioned, that you have the entire dynamic range mapped into 16 possibilities. So you are saying, I will divide the entire dynamic range into 16 chunks. So all these is going to be this number, all these will going to be this number. And this may still be okay, depend, because all your large language model would do is that it will point to a vector, and that is the vector for the or index, which is the next word. But floating point is where you have 16-bit divided into three parts. Okay. First part is the sign. If it is negative number, you are going to put a 1 here. If it is a positive number, you are going to put a 0 here. And then is the exponential. And that basically helps you to do the dynamic range. And these are, let's say, 5 bits are for the exponential. So you are always going to write a number as a sign, whatever, and then let's say 2 raised to the power something is the exponential part, and then you have the fractional part. So 1 is implied, so 1 you don't even write, and this is the decimal part. All the floating point numbers are. So you are always going to have a number. Let's say it is 100 point something. So you got to move this 100.456 into 1.456. So and this becomes a lot of complexity into actually implementing it in hardware. So you have 100.14. I'm just giving you an example. Okay, but to represent them, your number should always be 1 point something, and whatever you want to take it on the exponential, you take it on the exponential. So you put it here, 2 raised to the power something. So that is why you can represent a lot bigger dynamic range, because of every time, whatever the answer you get, you are going to push it onto the exponential, the power, and that will help you to have very big number and very small number, power going negative, power going positive, power going negative, and still having decent uh, precision for the fractional part, which comes here. But every time doing this would take number of cycles. Every time you get a number, you check whether it is in the standard format or not. If not, you need to convert it by figuring out how much has to be shifted, shifting it that much, taking it to the exponential. Then exponential also has a bias. So, so doing a lot of this actually do the representation. So, for example, here is a number which is, and also remember that the memory is just 16-bit. It has no way of knowing that this is how you are perceiving the 16-bit, that this bit is this. It is because this is in your perception, and the hardware you have designed would deal with these bits as these are the exponential, this is the sign bit, these are the fractional bits. So once you see uh, a memory content, a 16-bit memory content written as 0 1 0 0 0 1 0 0 1 0 0 1 0 0 0. So this is the sign bit, means positive number. So -1 raised to the power 0 will make this number a positive number. So it's either is going to be a positive number or a negative number. And remember this, whatever is this number, it is 2 raised to the power -1, power is 0.5, 0.25. These are the weights of the fractional part going to -10. So, and this one is implied, which is always 1 point something is the format this. And here is the power. So it is, there is a bias as well. So this is 1 0 0 0 0 0. It is actually exponential is 2 raised to the power 4, and 4 is 16, and then there is a bias. So ultimately, if you do exponential minus bias is something 1, so it is 2 raised to the power 1. So the number is 3.140625. So this 3, in order to convert it into 1 point something, it has been raised. This exponential is put into some part of it is put into the exponential, and there is this format where they have a bias also, which you need to take out from the representation, or you need to add it into the representation to represent. And because bias is 15 and this is 1, so you need to make it 16. So what you write here is 16. So that is something which 1, 2, 4, 8, 16. So this is 16 that you have to write, and actually it is 2 raised to the power 1, and for some reason IEEE format add the bias into the number, it becomes. And if it is a 32-bit, so then 1 bit is the sign bit, and then 1, 2, 3, 4, 1, 2, 3, 4. 8 bits are for the exponential, so you can have a bigger exponential. And rest of these bits are the fractional bits. The same thing, there is a bias, and then there is and so this is the representation. So in that case, the bias is whatever the 2 raised to by 8 minus 1 is. So that is the bias. So you write it like this. So the same number as a 32-bit precision. Now you start seeing many of these because of uh, all these numbers which are there in the fractional part. So a same number as a 32-bit precision and same number as a 16-bit precision. So these are the two different numbers representing as a floating point format. Now comes the what is the difference? The difference is uh, important is the precision. So here you have like more precision, here you have the less precision. This is one difference in the and the minimum value that you can represent is because of the exponential, and so, and this is the maximum value that you can represent is minus 3.8 and plus 3.8 exponential e raised to the power 38, e raised to the power 38. Then many large language models, they use another format, which is BF16 format. Because of increased dynamic range, they want to assign more bits to the exponential part, the same as is in 32-bit precision. So, and and because of that, it covers the same kind of the dynamic range as is 32-bit number, but you are though losing some precision here in the fractional part, which is the 7-bit and 8-bit and the sign bit. So many large language model, they use BF16 format, where they, instead of the IEEE floating point format, they have more bits in the exponential form. Now comes the the fixed point. In fixed point, you have, if it is int 8, there are only 8 bits. 1 bit goes to the sign as 2's complement. Now you have 7 bits. So you have total of 256 values. It means that everything, all these infinite possibilities of numbers are to be mapped, number from minus 127 to 127. Okay, so that means many of these will be mapped onto just one number, because there are only going to be 256 possibilities. And obviously, for this case, they are going to be 2 raised to the power. But that is not important. Important is because of this exponential, you can still somehow capture the value of the number by pushing things onto the exponential. Here, that option is not there. The exponential is not there. So you have to fix the point of decimal. So as it goes above that number, it's going to overflow. As it goes below the number, it is going to underflow. So it becomes challenging. Uh, and or as I mentioned, that you have to have all these values mapped onto one number, all these value maps. So you have the entire dynamic range mapped to something which is fixed. So these are the differences, that you have a floating point 32, you have a floating point 16, you have a BF 16, and then you have a fixed point integer format, which has its own dynamic range as an integer number. And you need to decide that uh, how are you going to represent these numbers. So as you can see, here is the negative number and the positive number, the minimum and maximum, what all is possible. And so once we say it's a 70 billion parameter model, and if you are using 64-bit precision, so this is the amount of memory required, 560 gigabyte. Not possible that every prompt, like we are generating the prompt, has to go through 560 gigabyte of data just to generate one word. Okay, in this case, it's a 200 gigabyte, or for 16-bit it is 140 gigabytes. So that's why people are very keen to do the quantization of all the parameters, so that uh, first, it takes less memory. Second, all the computations can be simplified. So fixed point conversion is definitely an option. And fixed point conversion means that you need to decide about the place of decimal. So we have seen that how the floating point number works, what is the IEEE 32-bit floating point format, and what are the challenges. Okay, and especially in addition, in multiplication, always bringing every result back. And once you have exponentials, you are multiplying, exponentials are to be added, fractional part are to be multiplied, signs are to be multiplied. Then you're going to see that what you have. And same is the case with addition. First, both the exponential should be aligned, only then you can add numbers. So you need to do the alignment, then you are adding, then the result you are going to again move. So it's a lot of things that you have to done in order to convert numbers, do the arithmetic in the floating point format. But fixed point is, uh, I'll be just finishing this lecture. So fixed point is that you say, Naiji, I cannot handle, that type of complexity. I just want number to multiply, get an answer, add, get an answer. I am not going to see before adding both exponentials are the same or not. Only then I add. So it's a lot of kind of complexity in addition and multiplication. So you say, what if I fix the place of decimal, and then make a number integer? And this I remember by in a command that actually there is a decimal, and ensuring every number that I'm adding has a decimal at this location, because that's how I have converted a number into a fixed point format. And this format is called qn.m format, with where n numbers are on the left side of the decimal and m numbers are on the right side of the decimal. And this is how they actually are weighted: 2 raised to the power 0, most significant bit has negative weight, and all the bits on the other side have fractional weight: 2 raised to the power -1, -2, -3, -4, -5. So that is where it's the same thing that I told you. So conversion is that once, if I want a fixed point implementation of a number, I need to decide about. Actually, it is very simple that you write a number in binary format, and you put a decimal here, and then you have this number, and then you have this number. And let's say you want to fix this decimal at fourth place. Okay, so there's already a decimal point here, and you are going to place it after 4. There are 4 bits at the integer part, so you're going to have a sign bit extended to this, so that always the you have fixed number of bits for the integer part and fixed number of bits for the fractional part. and there is no exponential because you have fixed the decimal point and you are keep tracking it throughout your computation. So in this case, if a number is written like this and it is two dots some format, so it is actually 1.8125 because this has a positive weight of 1, and these all these bits have fractional weights of half, 1 by 4, 1 by 8. So this is what the number becomes, and hexadecimal it will look like this. So this as an integer would be some number, and as a hexadecimal it will be this number. So fixed point conversion of variable is very, very important from hardware perspective. Q to dot and format. I think that's pretty much what I wanted to cover. If you have any question, uh, I've already shared like दो questions आपके लिए थे. I'll share a few more questions. And I also want to give you an assignment which you may try for the exam as well. जिस तरह से FIFO था ना, I would like you to generate a code for a LIFO where last in first out on the same, following the same guidelines, and try to generate a code for uh, लास्ट इन जो स्टैक जिसको कहते हैं, लास्ट पुश होता है वो सबसे पहले, लास्ट इन फर्स्ट आउट लाइफ हो, वो आपने करना है. और इंशाल्लाह बेस्ट ऑफ लक फॉर योर एग्जाम. कोई क्वेश्चन हो तो आप मुझसे कर सकते हैं. So if there are no questions, thank you very much. Inshallah, we see each other after the exam, which is next to next week. And I'll try, if I'm there, I will also try to be there for your exam. Thank you, ji. Assalamu alaikum.
Thank you, sir. Allah Hafiz.
Thank you, sir. Assalamu alaikum.
Walaikum assalam.